Hi, today we're going to be taking a look at rolling with slipping. And I think it's hard to kind of visualize what that means. But what happens is something starts by slipping, and then because friction is acting, because it's slipping, but not like frictionlessly, then it slows down and eventually it gets slow enough that friction is enough to just make it rotate instead of slide. So I'm going to show you this video of bowling, which shows this really well, that it starts by slipping and then it slows down until it starts gripping and rolling. And there you go. And so you can see that um, is sliding and then rolling. So now what we're going to do is take a look at how you deal with calculating that and what it is you're actually going to calculate if you have to calculate that. I've only seen a problem like this on the AP exam once in all of the history of APC, which is a long time. So this isn't something that I would completely stress out about, but on the other hand, I really want you to see it just in case. It's not really all that hard. So here we go. First step is to draw a free body diagram and write your force and torque equations just like usual. And the key thing here is that it's going to slide until the speed is slow enough that it rotates. So until this condition is met, that V is equal to omega R, so that the translational speed is equal to the rotational speed times the radius. So the strategy is, from your free body diagram and force equation, you're going to get an equation for A, an expression for acceleration, and then you're going to plug that into an equation for V. Then, from your torque equation, you're going to get an expression for alpha. This is different than we've done before. Usually we use alpha is equal to A over R, and then our R's cancel and stuff. Here, we're actually going to solve for alpha. And then once you have alpha, you're going to plug that into the rotational version of that same equation. Omega is equal to alpha t plus omega 0. But omega 0 is 0. Since it isn't rolling yet, it was just sliding. And then you set those two things equal to each other. What that does is it allows you to get an equation that has only one variable in it, t. So you can solve for the time it takes in order for it to stop sliding and start rolling. Once you have that time, you can solve for all sorts of other stuff. You can solve for the distance it travels before it starts rolling. You can solve for the speed it gets to before it starts rolling. But that time is the key part. You need to solve for time first. So I'm going to go through an example of this so that you can see what I'm talking about. So here we go. Here's a problem. So we have a 0.5 kilogram billiard ball, so not a bowling ball in this case, and we're going to, it's got a radius of 0.1 meters. You probably have a pretty good idea at this point that we don't care about the radius anymore, that it will cancel. It's hit so that it skids with an initial speed of 4 meters per second. The coefficient of friction on the table is 0.25. We want to know how long it takes until the ball starts rolling. So we're looking for the time. So first step, as always, is free body diagram. So there's our billiard ball. Our forces that are acting on it, we're going to have the weight. We're going to have the normal force. And we're going to have friction that's acting. I'm going to say that it's moving to the right. So I'm going to make to the right be positive. So first step is I'm going to write the sum of my forces is equal to MA. I have the x direction, I only have friction. And that's going to be equal to MA. In the y direction, I'm going to have normal force minus mg is equal to MA, but in the y direction, it shouldn't be moving anywhere, so that should be 0. That means that the normal force equals mg. Now, this is an oldie but a goodie. We haven't dealt with this equation for a really long time. The frictional force is equal to mu times the normal force. Remember that? That was a long time ago. And that is equal to mu, oops, forgot an equal sign, there we go, equals mu times mg. Because our normal force was equal to mg. So now what I'm going to do is I'm going to combine this equation and this equation. Since both of those are equal to each other, I'm going to have MA is equal to mu mg. Yay, M cancels. And now I have an expression for A. That's going to be mu g. So I'm going to use that expression of A in my equation here. V is equal to V0 plus AT. Now the trick is my V is headed to the right in the picture that I've drawn here, but my acceleration is headed to the left because that's the direction my force is going in. That means that my acceleration in this equation has to be negative. So V is equal to V0 minus mu g. So that is one of the equations that I need. Next up is torque. So the sum of my torques is equal to I alpha. The only force here that can cause a torque is frictional force, because remember that torque is equal to Rf sine theta. So the radius arm distance, so that's the distance from where it's rotating, so that's the center of this sphere, the force that's causing it to rotate times the sine of the angle between it. So from the center, the axis of rotation of this billiard ball, the normal force is acting in exactly the same direction as the radius. mg also acting in exactly the same direction as the radius. That means that the angle is 0 between those, so the sine of 0 is 0, and there's no torque. Those can't make it rotate. Only the friction is acting at an angle to the radius, and that's 90 degrees. So that's the only one that can cause it to rotate. And in this case, because it's 90 degrees, that means the sine of theta is equal to 1. So we don't have to worry about that angle. Yay. So our torque is going to be equal to the radius, which I'll use as capital R. And our force causing that torque is friction. So that's the left-hand side of the equation. I is 2/5, sorry, dinner's ready, 2/5 mr squared. And then usually I would do A over R, but I need alpha, so I'm going to leave alpha in there. Now I'm going to cancel whatever I can cancel. So R is equal to frictional force, but friction is mu mg. So that's 2/5 mr squared. That means that our m is going to cancel, and one of our r's is going to cancel. So that's pretty cool. So we have mu g is equal to 2/5 r alpha. Now what we really need is alpha. So to solve for that, rearranging that equation, I'm going to have 5 and mu g over 2r is equal to alpha. So now we're getting there. Omega is equal to omega 0 plus alpha t. Omega 0 was 0 because it wasn't rolling initially. So we've got omega is equal to alpha, which is 5 mu g over 2r times t. And that's the other magic equation that we needed. So now we take those two equations and we plug them into this. V is equal to omega r. So we have V0 minus mu g is equal to omega, which is 5 mu g over 2r times r. And now those r's cancel, which, you know, you had a suspicion that that was going to happen. So, and the I left out a t. So let me erase and fix that. And this is going to be a t. Sorry about that. So we've got V0 minus mu gt is equal to 5 mu g over 2r t times r. R's cancel. Our next step is to solve for t. Now, fortunately, in this problem, we have numbers. So we can plug numbers in and make this look less horrible, and then solve for t with just numbers. If you don't, it's algebra and it's a mess, but it's still doable. So let's put some numbers in because we can. So we have 4 minus, our mu is 0.25, g is 9.8, and then times t is equal to 5 times 0.25 times 9.8 divided by 2 times t. That's going to give us 4 minus 2.45 is equal to 6.125. We can add the 0.24 to each side. That gives us 4 is equal to 8.575. And t is then equal to 0.47 seconds. With that, we could figure out how long did it travel, or how far did it travel? We now know t. We know what V0 is. We know what A is because we figured that out earlier. So we could figure that out if we needed to, now that we have t. We could also figure out how fast it's going. Oh, whoops. Let me erase that. Let me try that again. So we could also figure out how fast it's traveling when it starts rolling. We have acceleration, we have V0, we have t. So then you can figure out how fast that's going. Remember to stick the negative sign in there for both of these because the acceleration is negative, it's slowing down in the direction that it's moving. But that's really all there is to it. So again, recapping, free body diagram, force equation. Figure out your acceleration by setting the two friction equations equal to each other. Plug it into V equals V0 plus AT. Because it's rolling, we also get to do a torque equation. Keep acceleration, the angular acceleration in there. Don't change that to regular acceleration. Stuff cancels, and you can solve for the rotational acceleration. Plug that into your omega equals omega 0 plus alpha t. Omega 0 is 0 at the start. Then this condition is what allows you to solve for t. So V is equal to omega r. When you set those, plug those things in, you can then solve for t. Once you have t, you can get anything else.